Welcome to the Explainer. Think of your Cambridge 0580 mathematics exam like the ultimate high-stakes vault. To pull off the perfect score, you can't just smash the door down. You need to assemble a team of cognitive specialists and execute a flawless strategy. Today, we are transforming a massive, potentially overwhelming glossary of geometric terms into your ultimate heist blueprint. I see so many students mess this up. Take a student we'll call Alex. Alex overloads his answers with raw, unfiltered mathematical facts, tossing every theorem he knows onto the page without analyzing what the question actually wants. Then you have Sam. Sam rushes the process, completely missing the specific command words the examiner uses to guide you to the marks. Today, we're fixing both of those approaches. We're starting from a single, dimensionless dot and building all the way up to a complex three-dimensional universe, showing you exactly how top students structure their geometry answers. Let's dive in and crack this open.
Because we have a lot of ground to cover to get you those top marks, here is our structural blueprint, our dimensional ladder. We'll start with Phase 1, the 0 to 1 dimension, setting the ground rules. Phase 2, angles, lines, and bearings, where we decode the examiner's specific language. Phase 3, 2D polygons and circles. Phase 4, entering the third dimension. And finally, Phase 5, congruence and similarity, the area where most students drop massive marks.
Section 1, the 0 to 1 dimension. Let's look at the absolute foundational building blocks of the exam. To pull off the perfect geometry answer, you first have to deeply understand the concept of a dimension. A dimension dictates exactly how a shape can be measured. It's the measurable extent of an object, like its length, its width, or its height. Now, this might seem incredibly basic, but misunderstanding this foundational concept is exactly where Sam rushes and loses points. If the command word says, calculate the perimeter, you're dealing with one dimension. If you accidentally apply a two-dimensional area formula because you didn't analyze the command word, your heist is over before it even begins. If you don't know what dimensions you're working with, you absolutely cannot calculate anything accurately. This brilliantly illustrates our geometric escalation. Look closely at how we build reality step by step. We start at 0. A point is simply a position in space. It has absolutely 0 dimensions. It's just a coordinate. But if you take that point and drag it, you stretch it into a one-dimensional line, which gives you length but 0 width. Now, take that line and pull it sideways, and you expand it into a two-dimensional plane, a completely flat surface with length and width but no height. Finally, if you take that flat plane and push it upward into the air, you pop it out into a three-dimensional solid, which possesses length, width, and height. This 0 to 3 progression is the hidden scaffolding behind every single geometry question on your Cambridge paper. Section 2, angles, lines, and bearings. Let's escalate our strategy and see what happens when those one-dimensional lines interact. Angles are the absolute foundation of shape interaction, and they're heavily tested. When two lines meet at a point, they create an angle. To describe and measure these interactions perfectly, we use a circular scale marked in degrees. The master key here is 360. One whole complete turn is exactly 360 degrees. Therefore, standard logic dictates that a straight line, a half turn, is perfectly 180 degrees. And a quarter turn, which creates a precise corner, is exactly 90 degrees. This is your rotational baseline, your anchor for solving any complex geometric puzzle. Now, what's crucial here is how we specifically categorize and name these interactions. Using the wrong term guarantees you'll lose marks. Angles less than a 90-degree quarter term are sharp, called acute angles. If it's wider than 90 but strictly less than a 180 degrees straight line, it's an obtuse angle. If it bends backward past that 180 degree straight line, it's a reflex angle. We also need to label the lines themselves. Lines marked with arrows that travel side by side and will never meet are parallel. Lines intersecting to form a perfect 90-degree cross are perpendicular. Remember Alex? Alex would write a huge paragraph about lines here. The top-tier strategy is simply applying the Peel framework. Point out the type of angle, evidence it from the diagram, explain your working, and link it to the command word. Boom, full marks. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the strategy. When we take these mathematical angles out into the real physical world for navigation, we call them bearings. Bearings are notoriously tricky because they act like a lock combination with 3 unbreakable rules. First, a bearing is always measured from a straight-up north line. Second, you must always measure the angle turning clockwise. And third, this is the exact spot where Sam rushes and drops a whole grade boundary. A bearing must always be written using exactly 3 digits. Even if the angle is just 60 degrees, you must write it as 060 degrees.
Missing that 0 means missing the mark. Section 3. 2D polygons and circles. Let's move to the second dimension and crack the code on flat shapes.
Let's start with the simplest closed shape, the three-sided triangle. The precise vocabulary here is critical. If all three sides and angles are completely different, it's a scaling triangle. If two sides and two angles match perfectly, it's an isosceles triangle. If all three sides are perfectly equal, it's an equilateral triangle. But triangles are just the warm-up. Any closed shape formed entirely by straight lines is classified as a polygon. We scale this up fast. A 5-sided shape is a pentagon, 6 is a hexagon, 8 is an octagon, and a massive 10-sided shape is a decagon. The moment you enclose straight lines, you have a polygon, and specific geometric rules instantly apply.
Stop and study this. This matrix is your ultimate cheat sheet for 4-sided polygons, known as quadrilaterals. It is absolutely crucial to know the subtle differences to bypass the examiner's traps. A square and a rectangle both have all 90-degree angles, right? But a square has all equal sides, while a rectangle only has opposite sides equal. Look at the parallelogram. Opposite sides are equal and parallel, but if you make all 4 sides of that parallelogram equal, it transforms into a rhombus. Here is the real insider secret. Look at their diagonals. In a square and a rhombus, those diagonals cross and bisect each other at a perfect 90 degrees. Knowing these hidden diagonal properties is how you transform a complex proof from a 0 into full marks in seconds.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's talk about the word regular in a geometric context. True geometric perfection in 2D happens only in a regular polygon. This means that absolutely every side is the exact same length and every single interior angle is the exact same size. A square is a regular quadrilateral. But listen closely. If even one side is slightly longer, or if just one angle deviates by a fraction of a degree, the shape instantly loses its status and becomes an irregular polygon. Now, when we leave the rigid world of straight lines entirely behind, we enter the territory of the circle. A circle is beautifully simple, but packed with highly specific vocabulary that examiners love to test. It is defined entirely by a center point and a radius, the distance from the center to the edge. Double that radius and you have the diameter, cutting completely across the shape. The full perimeter is the circumference. But watch out for the terms that always trip up rushed students like Sam. A line crossing the circle that doesn't pass through the center is a chord. And if a line just barely grazes the absolute outside edge of the circumference at a single precise point, that is a tangent. Section 4, entering the third dimension. We've mastered the flat plane, so it's time for an interactive workshop. Let's pull these shapes up and out into the 3D world. Welcome to Challenge 1, Find the Flaw. Look at how our terminology evolves here. What was once a flat 2D shape like a rectangle now becomes a solid flat surface called a face. The straight 1D lines where those faces meet are now called edges, and the sharp points where 3 or more edges crash together, those are vertices. This cuboid perfectly illustrates this. The flaw most students make is forgetting the hidden aspects. You have to train your brain to see the dashed lines in the back of the cube. If you're asked to count vertices and you only count the ones visible from the front angle, your answer is flawed, and the marks are gone. Challenge 2, Data Scan. Notice the incredible variety we unlock in 3D. We have solids with curved surfaces, like spheres or cylinders that combine flat circular bases with curved faces. But then we have the structural powerhouses, prisms and pyramids. A prism is defined by having the exact same cross-section all the way through. If you slice a triangular prism perfectly down the middle, you get that exact same triangle shape. A pyramid, on the other hand, starts with a flat polygonal base and has triangular faces that taper up to meet at a single sharp vertex at the top. The strategy? Scan the shape immediately to determine if it maintains its cross-section or tapers. That dictates your entire calculation pathway. Challenge 3, Speed Visualization. I want you to imagine taking scissors, cutting along the edges of a box, and laying it completely flat. That two-dimensional blueprint is called a net. This brilliantly illustrates the direct link between 2D and 3D. A net is a flat arrangement of faces that, when folded correctly, perfectly constructs a 3-dimensional solid without any overlaps or gaps.
In the exam, you will frequently be given a complex net, and you'll have about 60 seconds to mentally fold it in your head to identify if it creates a cube, a pyramid, or a prism. Practice this mental gymnastics. It's a massive time saver. Section 5, Congruence and Similarity. We've reached the final vault. This is the advanced geometric language used to compare two different shapes. The absolute crucial point here is grasping the rigid distinction between these two terms, congruent and similar. If two shapes are congruent, they are exact, identical clones. Every single corresponding angle matches perfectly, and every single corresponding side length is completely equal. They might be rotated or flipped to confuse you, but they are exactly the same size. However, if two shapes are similar, they share the exact same internal angles, so their overall shape is identical, but their sizes are different. In similar shapes, the side lengths are completely in proportion, representing an exact mathematical enlargement or reduction. Mixing these two up is a classic high-cost error.
If you look at these visualizations, you can see this concept in action. On the left, we see congruent triangles. Even though some are upside down, if you cut them out, they would stack flawlessly on top of one another, with no edges sticking out. Now look at the similar shapes on the right. The angles in the small quadrilateral precisely match the angles in the large one, but the side lengths are stretched. This stretch is governed by a scale factor. If every side in shape B is exactly 2 times longer than shape A, then shape B is an enlargement of shape A with a scale factor of 2. Identifying that scale factor is the key to unlocking the final marks on your paper.
Ultimately, our mathematics success blueprint comes down to 3 rules. First, command word decoding. Know exactly what the examiner is asking. Second, applying the Peel framework. Make your point, give evidence from the shape, execute the formula, and link to the final answer. Third, mastering your time management matrix so you don't rush like Sam or overcomplicate like Alex. Geometry is the invisible, highly structured mathematical framework of your entire physical world. Look around your room right now. Intersecting planes, 90-degree vertices, and 3D solids construct your reality. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.